that is basically how we establish this medullary osmotic gradient. That is the first part of that. The second part of establishing the medullary osmotic gradient brings into question urea. Now, urea is a molecule that's generated by the liver. It's actually a waste product. It's a byproduct or a breakdown product, rather, of protein. So protein is a nitrogenous structure. And when we break down that protein and liberate our amino acids, urea is the form that we eliminate most of that nitrogen as. It is water soluble, so it can move freely through water structures, but it cannot move through our membranes, right? Remember, our membranes are lipid soluble structures, and so anything that's water soluble will not be able to move through our membranes. Therefore, it requires transporters. It's going to require transporters UTA, UTB, and UTC. These are placed at different strategic locations throughout the nephron, okay? You don't have to go into the detail here, but for the purpose of understanding this, I'll explain. UTC is found in the proximal convoluted tubule. UTB is found in the descending limb, of the vasa recta. And then UTA is found in the collecting duct, okay? And the strategic locations of these transporters is going to be important to facilitating water reabsorption and to maintaining the medullary osmotic gradient, all right? So the transport of urea through UTA in the collecting duct is what facilitates the reabsorption of water, right? So because urea has this osmotic pull, it behaves just like our other solutes and just like proteins, where wherever it goes, water follows it. And because we have these transporters for UTA on the collecting duct, we can facilitate the movement of urea through the collecting duct, and then water will simply follow that movement of urea. It has that osmotic pull that we talked about. And that is also going to be important in maintaining the medullary osmotic gradient. So this deeper part of the medulla is going to have a more concentrated osmolarity than the cortical areas or the proximal areas of the kidney, of the nephron. The other important thing that I want to point out here is the anatomical orientation of the vasa recta. So we spoke about the vasa recta. We said that it's this network of capillaries that kind of entangles or interweaves around the loop of Henle. And I want to point out here, because this is often a point of confusion, that the loop of Henle, which is the tubular structure, goes from the proximal convoluted tubule, and the direction of flow is going in this direction towards the distal convoluted tubule. But the vasa recta is kind of flip-flopped. So the vasa recta has a direction of flow that is opposite to the flow of the tubular fluid that's happening in the lumen of the tubular structures. So the blood that's flowing in the vasa recta goes from this region, right? This is our afferent arteriole. Efferent arteriole, right? This is coming out the end of the glomerulus. It's going to go in this direction. It's going to come in contact with the ascending limb of the loop of Henle, right? And then the descending limb of the loop of Henle. So we can also describe the ascending and descending limb of the vasa recta as well. And they're going to be in the opposite orientation to what we see in the tubular structures. So blood is flowing down the descending limb of the vasa recta, which comes in contact with the ascending limb of the loop of Henle, and blood is flowing from the ascending limb of the vasa recta, which is coming in contact with the descending limb of the loop of Henle. So make sure you're bearing that flip-flop in mind in terms of the bidirectional flow in the vasa recta and what's happening in the lumen of the tubule, the loop of Henle. Okay, all right. Now, let's speak about how that orientation, that anatomical arrangement of the vasa recta, that flip-flopping, how that is important in maintaining the medullary osmotic gradient. So we talked a lot about how we establish that gradient and why that gradient is important for the reabsorption of water. But let's speak about how we keep that gradient, kind of lock that gradient into place and prevent the dissipation or the dissolution of that gradient via the unique anatomical arrangement of the vasa recta. So this is looking at the vasa recta here. So I don't want you to be confused. This is not the tubule. This is the vasa recta, which is a blood vessel. This is where blood is flowing. And this is, again, going in the opposite direction of what we saw with the tubule. So this is the descending limb of the vasa recta, which comes in contact with the ascending limb of the loop of Henle. And this is the ascending limb of the vasa recta, which comes in contact with the descending limb of the loop of Henle. All right, if you're not looking at the flip-flop orientation of this, it's going to be a little bit confusing. So make sure you're bearing that in mind. And so the descending limb we know has an osmolarity of about 300 milliosmoles. And as it descends, water is going to be leaving the capillary. Remember, this is a capillary. Water is going to leave this capillary and go out into the medullary interstitial fluid. And solutes are going to be moving in the opposite direction. Solutes are going to be moving from the medullary interstitial fluid and into the descending limb of the vasa recta. Okay. Now, the reason we have this is because of the unique location of our urea transporters. We do not have urea transporters on the descending limb of the vasa recta. And I'll jump back here just to point that out. So if we can see, this is the vasa recta. This is the descending limb. Okay, I'm sorry, I think I just flip-flopped that. So we have urea transporters only on the descending limb of the vasa recta, which is the ascending limb of the loop of Henle, and we do not have urea transporters on the ascending limb of the vasa recta. Okay, so make sure you're making that clarification. And so basically we can move urea through the descending limb. And remember I said urea has this osmotic pull. So if I am able to move urea through the descending limb because of the fact that I've got transporters for urea, then water will move across the descending limb. So water is moving out of the descending limb, the capillary here, and into the osmotic, medullary interstitial fluid, whereas solutes are moving in the opposite direction. Solutes are moving from the interstitial fluid and back into the capillary, into the vasa recta. And so we see that the osmolarity is raising as we go down the interstitial, as we go down the vasa recta, the descending limb of the vasa recta, okay? Now, as we go up the ascending limb of the vasa recta, the osmolarity here is going to decrease. And this is crucial to maintaining our medullary osmotic gradient. If we did not have this flip-flopping of the movement of water and solutes, then we would lose our medullary osmotic gradient. Really, really important point to make. Because water is moving out into the interstitial fluid, we tend to kind of dissolve that gradient, okay? And so as we move up the ascending limb, we're gonna have to reverse the direction of water and solutes. So as you can see, up the ascending limb, water is moving into the tubule, which is the opposite of what happened in the descending limb, and solutes are moving out of the tubule in order to reestablish that medullary osmotic gradient, okay? So if we were only moving water out of the tubule, out of the vasa recta, throughout the entire length of the vasa recta, then it would completely water down or completely dissipate or completely dissolve our gradient. And that is not what we want. We want to maintain a salty or more concentrated area down here in the medulla and a little bit more of a dilute area up here as you get closer to the cortex, okay? So vital to maintaining that medullary osmotic gradient that we worked so hard to establish, we must have, one, this unique anatomical arrangement of the vasa recta, where we have this flip-flopping in terms of the direction of flow. And two, we must have a descending limb that is permeable to urea, but an ascending limb that is not permeable to urea, okay? Really, really important to understand that, how we keep that gradient in place. Right. All right, let's see a few questions here. Can you re-explain what is opposite about the direction of the vasa recta from the tubule? Oh, so someone said they got it. Okay. And I'll just double check. I'll just double back and explain that again, just for those who may have missed it. So the bidirectional flow that I was talking about is understanding that flow through the vasa recta is moving in this direction. We can kind of think of it, as going backwards, right? Whereas flow in the tubule itself is moving in this direction, okay? So as we go back here and make a little bit more sense of that, we see that this is coming in contact. This descending limb of the vasa recta comes into contact with the ascending limb of the loop of Henle. And so as we're reabsorbing solutes from the ascending limb of the loop of Henle, we reabsorb those solutes into the descending limb of the vasa recta. And on the other side, we see the opposite is true. As we reabsorb water from the descending limb of the loop of Henle, we reabsorb that water into the ascending limb of the vasa recta. And this is facilitated because of that bidirectional flow that we see between the vasa recta and the loop of Henle, okay? I hope that made a little bit more sense. All right. So now we're gonna kind of summarize all that we've spoken about and talk about how the distal parts of the nephron have a more regulated reabsorption of water. And this is a summary of how water is reabsorbed through the entire nephron. So we saw that 70% of water is reabsorbed in the proximal tubule. This is not regulated. This happens via solute reabsorption. And we said that that water simply followed. Now, in the distal parts of the tubule, I want you to make this note here just so that you're not confused. Now, your textbook kind of lumps all of this 20%, which includes what happens in the descending limb of the loop of Henle. But I want you to make a distinction that the descending limb, the water reabsorption that happens in the descending limb of the loop of Henle is not regulated by ADH, okay? So although we're kind of collectively looking at this 20% that happens in the distal part of the tubule, we're going to be including what happens in the descending limb of the loop of Henle, but it is not regulated by ADH, right? It happens freely according to that medullary osmotic gradient. And then the final 10% here, which is reabsorbing in the collecting duct, that is the distalmost part of the tubular structures. This is very much regulated by ADH. So what happens in the distal convoluted tubule and what happens in the collecting duct is going to be regulated based upon external factors, things like our hydration status, things like our GFR, things like our higher centers in the brain, our thirst centers. So if you're feeling more thirsty because of the signals that are relayed to those higher centers of the brain, we're going to secrete more ADH and we're going to reabsorb more water. So we can see how this will be regulated, whereas the proximal parts of the tubule are not regulated. They're just freely reabsorbing water.